I'm going to start with a couple of quick errata from the previous parts. I can't remember when I told you how to calculate. So when I told you how to calculate a term from the, when I told you how to calculate expectation value of little h on a pair of sites, and I drew you the diagram for that, I can't remember if I included these lambdas out on the edge here in the diagram. So just to make sure, telling you now that you do need to have those in there. Okay, great, I did, that's fine. It's pretty easy to see why, because if you start at the edge, then these guys reduce to the identity, and then, oops, got that the wrong way around already. Then you have something like this, and this reduces to the identity as well, and so on, and until you rub out the last pair here, and their associated diamonds, their associated lambdas, and you're left with these ones still intact. So that was just that little comment that those ones are still going to be in there when you work out expectation value of little h on a pair of sites. Other thing to mention, when I was talking about the mirror last week, I drew you up a 3-to-1 mirror, and I made a comment about how we usually assume that within a row, all the disentanglers and isometries are the same. This is only true when we're working with periodic boundary conditions. Now, the diagram I drew for you last week, which I'm just drawing again, is for open boundary conditions. You can't make that assumption in this case. You've got to treat each disentangler and isometry in the row as being different and optimize them all individually. But when you're working with periodic boundary conditions, you basically have another disentangler up here, which connects to this one, which connects over here, like so, and we have another disentangler over this side, which also connects around the boundary. And in this case, you have periodic boundary conditions, and if you have a translation invariant Hamiltonian, then it is perfectly reasonable to assume that all the disentanglers are the same on a row, all the isometries are the same on a row. And finally, when you get to the top, you're going to have two terms in the Hamiltonian when you lift them up to the final two, when you work out the effective Hamiltonian on the final two-site lattice, which is what you get by lifting little h from row to row. You're going to have two terms. You're going to have a term on two sites like that, and you're going to have a term which goes around the boundary like that. Now, by translation invariance, these guys are going to be identical, so you can just work out this one, and then add to it, the same thing with the two indices interchanged to get the total Hamiltonian at the top. And that's what you then diagonalize to get the top tensor. So just worth pointing that out. Yeah, okay. That's a quick recap of important things that came up over the last couple of talks. So
how many iterations do you have to go through sampling all of these things, all these tensors?
It very much depends upon the Hamiltonian you're studying. For some of the conformal, and also there's lots of tricks you can put in to make it converge faster. To get really nice results on some of the conformal field theory stuff, I've let it run for maybe 10, 15,000 iterations. That's basically, by that stage, it's usually stabilized to about 10, 11, 12 decimal places. But that's seldom necessary because that's actually, you're getting your results stable to far more decimal places than it's accurate. So it's like
That's the energy to that many decimal places, you're saying?
That was the energy to that many decimal places. The scaling dimensions, when you're doing scale-invariant mirror, they do tend to take longer than the energy does to stabilize. So you have to keep an eye on all of these things. Easiest way to do that is just to compute them every 10, 15 iterations and print them out. So this week I've decided what I'm going to do is I'm going to talk a little bit more about the scale-invariant mirror, because I rushed through that very quickly at the end of last week. And I'm also going to probably mention briefly the boundary mirror for boundary conformal field theory. So before I start, any questions about the stuff we've covered so far? Because the stuff we've covered is basic tensor networks, how to do TEBD, which is the assignment, and quick introduction to mirror, which will get rehashed slightly when I talk about the scale-invariant one. All good? Okay, so scale-invariant mirror. Now, as I mentioned last time, the idea here with scale-invariant mirror is that you're studying a critical theory on an infinite lattice, and so what you're going to do is and so in theory what you'd have is an infinite number of layers of mirror. Now, with a critical theory, you have the property that you have the property of self-similarity, in that if you look at it at different length scales, then basically, crudely, to put it crudely, the theory looks basically the same at many different length scales. What this means in practice with the mirror is that you start off with some Hamiltonian on the lattice, on some sort of initial lattice, and then after you coarse grain a few times, your Hamiltonian rapidly converges towards a particular Hamiltonian, which we call the fixed point Hamiltonian, and then remains the same under all further coarse grainings beyond that point. That is, once your mirror has converged to an accurate representation of the low energy subspace.
So that's only true at a critical point, right?
That's only true at fixed points of the real space renormalization group flow. That's critical points, product states, critical points, product states, and let's see, is it also true at, I think it's, I think it's also true, yes, it's also true for theories with topological characteristics such as Kitaev's toric code, where you don't actually end up in a product state, but you end up with a fixed, finite dimension, fixed subspace. So I'll put topological models. Basically, what these all have in common is that beyond a certain point, beyond a certain level of scaling out, you stop seeing the fine detail of the theory, and you only see these fixed point behaviors. So you can think of, if you like, a space of Hamiltonians, and what we have is we have our initial Hamiltonian somewhere in that space. And then within this space of Hamiltonians, under the real space renormalization group, which is a rescaling of your spatial coordinates, we have flows within the space of Hamiltonians. And these flows may they may create saddle points, they may create they may create points of convergence, or they may also be divergent points within this space. And what happens is you're going to start at some initial Hamiltonian, and because we're working with, and what you're going to do is you're going to perform a transformation on that Hamiltonian, which is going to basically map it along the flow until it reaches a fixed point, at which point any further coarse graining is going to leave it stuck at that fixed point. Very often, we'll actually start off somewhere near a saddle point, as we do, for example, with if you do the criticalizing model, you're actually starting near a saddle point, and you rapidly converge to the peak of that saddle. In theory, it's unstable, and you could fall off the saddle if you iterated for long enough and move to a different fixed point. In practice, this is the fixed point we're interested in, and our code tends to converge pretty well to that one as well. It heads in towards that fixed point, and then the rate at which iterations move the Hamiltonian along the flow, it probably doesn't hit the fixed point exactly, but the Hamiltonian is progressing along the flow so slowly that we say, oh, it's converged and it's reached the fixed point. So basically what we have is a way of taking an initial Hamiltonian that's not a fixed point Hamiltonian, but is critical, meaning that after you perform an initial number of coarse grainings, you flow to one of these fixed points. And then we can get to that fixed point and we can study the properties of the Hamiltonian there. So to do that, what we need to do is we need to start with our Hamiltonian and start with our initial bunch of random tensors for the mirror. And then we need to somehow optimize these tensors so that they represent coarse graining, a spatial coarse graining, so like every 3 sites into 1, that preserves the low energy subspace of that Hamiltonian. And we need to do so for an infinite number of layers. Once we've got this mirror structure that preserves the low energy subspace of the Hamiltonian, then we're going to and we're mapping from a space of dimension chi to dimension chi, so chi cubed each time to chi. It's a property that so when we're at the fixed point, then in mapping from a dimension, then projecting from that space of dimension chi cubed on 3 sites to a space of dimension chi on 1 site, we find that basically each time we're fusing 3 subspaces, then projecting down onto a subspace which exactly resembles the one that we started off with before. So you've got this scale invariance going as you work your way up the mirror. So how do we actually optimize this? I talked about this briefly last time. What we do is, so first of all, we're not exactly at the critical point we want to get to when we start out. Our Hamiltonian is made up of types of terms called relevant, irrelevant, and, well, any operator is made up of terms called relevant, irrelevant, and marginal components. A relevant component grows under the action of the real space renormalization group transform. A marginal, well, grows faster than the Hamiltonian. A marginal operator scales the same as the Hamiltonian under this coarse graining, and an irrelevant operator scales less than the Hamiltonian. So as you repeatedly coarse grain, compared to the fixed point Hamiltonian, irrelevant operators, if you have a Hamiltonian that consists of a fixed point Hamiltonian plus a bunch of irrelevant terms, then under repeated coarse graining, those irrelevant terms are going to get suppressed until they're effectively eliminated, and that's your process of convergence. Your Hamiltonian defines the fixed point Hamiltonian defines what is meant by a marginal operator, and a critical Hamiltonian will have no relevant terms. Those would be terms that would sort of that would basically grow with respect to a sort of your nominal fixed point Hamiltonian. What this means is that if we took our critical Hamiltonian and we added And we add an irrelevant perturbation, then we're just moving from somewhere that flows to the fixed point to somewhere else that flows to the fixed point. We've just added another irrelevant term that's going to fade away. Marginal is a bit more tricky, tends to stick around. If you add a relevant perturbation, then you're moving effectively onto a different flow, something that no longer converges towards your original fixed point, and instead is going to converge to somewhere else, because you've got a term that grows under your real space renormalization group transform until effectively what you thought is that your original fixed point Hamiltonian is basically suppressed relevant to this. So there's three types of perturbation that you can. So if you have a critical Hamiltonian, there's three types of perturbation. Also, we know that our original fixed point Hamiltonian consists of only the fixed point Hamiltonian itself and irrelevant terms. So the first thing we want to do is we want to go from our critical Hamiltonian to our fixed point Hamiltonian. That means get rid of the irrelevant terms. We know that during this stage, the Hamiltonian is not going to be truly scale invariant. Each time we perform a coarse graining, it's going to have a little bit less of these irrelevant terms in it. So what we're going to do is we're going to perform a number of layers of mirror, which I'm just going to represent by a blob here. That represents your row of disentanglers and your row of isometries. We're going to perform we're going to apply a few layers of the mirror just to get rid of those initial irrelevant terms. And these are going to be sort of layers of the mirror in the normal sense. And then we're going to have our special layer of the mirror, which is our scale invariant layer. We assume that after these initial layers, we've reached a point where the irrelevant terms are completely suppressed. In practice, they're not going to be. It's an exponential suppression, but there's always going to be a little trace of them left. But we approximate that after some number of layers, they're suppressed sufficiently that we no longer care about them. They're effectively gone. And then we have the scale invariant layer, which is where we assume that the Hamiltonian is self-similar. And at that level, we do the trickery I talked about last time, and which I'll just review now, where you assume that this layer represents an infinite stack of layers. Now, worth pointing out here is that if you start with, say, a value of a physical dimension of 2, Hilbert space of dimension 2 on each site, then on your next layer, you can have a Hilbert space of dimension 8. On your next layer, you could go up to, say, set your upper limit on chi to be, say, 16. Then you're going to be going from 16 to 16. It's important that that the scale invariant layer should be a mapping from dimension. So if we call this chi 0, chi 1, chi 2, chi 3, chi 4, it's important that the scale invariant layer should constitute a mapping from sites of some fixed dimension chi s for scale invariant to sites of that same dimension, chi s again. And of course, it's an infinite mirror. Now, because we can think of let's see now then. Next thing to comment on. So mapping from, our scale invariant layer. I mentioned briefly last time how we computed the reduced density matrix that was invariant under lowering from we've got a hypothetical top reduced density matrix an infinite number of layers away, which we then bring down using the lowering procedure I described last time to the actual region of the lattice we're interested in working on. I explained to you last time how we computed this, which is that we took that set of 3 diagrams that described moving a reduced density matrix from one layer down to the layer below, and we diagonalize and that constitutes a super operator which we diagonalize to find the fixed point Hamiltonian. Now, a tip in practice for, so yes. basically what we're doing is we're diagonalizing the scaling superoperator, which looks like so we're diagonalizing this scaling superoperator, whoops, which lowers reduced density matrices and averages across the 3 possible directions they can be lowered because you've got translation invariance. Now, this is actually computationally costly. What we don't do, in practice, what we don't do is compute this scaling superoperator and then diagonalize it using, say, Landshaw's method or anything like that. That would be too expensive. For example, the 3-to-1 one-dimensional mirror I've been talking about, the cost of updating that mirror is of order chi to the 8. The cost of diagonalizing the scaling superoperator of computing the scaling superoperator is order chi to the 10. We did this at first when we were developing the algorithm. Then we realized that this is too expensive, and there's a better way of, well, first of all, instead of, it's like, to construct it exactly costs chi to the 10. To diagonalize it using Landshaw's method costs chi to the 8, because basically what you're doing is you're creating a trial reduced density matrix, lowering it, so you're computing this for a large number of reduced density matrices rho. So again, it's chi to the 8, but it's got a large prefactor. If you exactly diagonalize each time, then you're going to take a large number of these trial reduced density matrices and lower them to successfully diagonalize your scaling superoperator. Turns out we can do better than that, because especially at the beginning of the algorithm, especially when we're first starting to run our updates, we don't care about getting the diagonalization exact. Our U's and W's are a long way off convergence. And so we could spend a lot of time diagonalizing that exactly, only to basically throw it all out next time and more or less start again from scratch because U and W have changed so completely. Well, not completely, but they've changed a lot. And so we need a new row that's quite different. So instead what we did, we realized that for the mirror to converge, you have to have, so when the mirror has, a converged mirror will have a U and a W such that the reduced density matrix is not changed under lowering, and a reduced density matrix such that the U and the W are not changed when they're updated. That is when you do your diagram with the Hamiltonian in there and one of your tensors removed, and to compute an updated U or an updated W, that updated U or W is basically the same as the one you had before. Now, what we realized is that when this is true, is that if we take the reduced density matrix and instead of computing a new one by diagonalizing, if instead we just lower the old reduced density matrix once, to obtain the new reduced density matrix, like so. So basically what we do is we perform all our updates, starting from the bottom, working up. We update all the U's, W's, lifting the Hamiltonian up layer by layer as we go. and at each layer, we're using the reduced density matrix we have at that layer in the diagrams for updating U and W. We get to the very top, and then when we want to compute a new top reduced density matrix, we take the existing top one, so like row at the top, we lower it once to obtain the reduced density matrix as if we just lowered it through the scale invariant layer to get the new to get a new density matrix, row top minus 1, and then we take that to be the new row top. Once the mirror has converged, this process will have absolutely no effect on row top. And we found that this works very nicely. In practice, what tends to happen is that just lowering this once provides sufficient convergence of the reduced density matrix that the isometries that disentangle as the reduced density matrix, they all converge very nicely together. The cost is much lower. So the additional cost due to working hard on the reduced density matrix is eliminated, and you still get to your and you actually get to your final converged state much faster. In the end, of course, it's equally good because assuming as always that you don't wind up with a row that has absolutely no overlap with your true top reduced density matrix, is like in theory it's possible to wind up trapped at a different fixed point, which is not. It's possible in theory that you could have a reduced density matrix which is lowered and gives you back the same reduced density matrix and isometries which are preserved under that under the whole mirror. Basically, what you have is if all your approximations conspire against you, your finite number of layers, your finite chi, your initial starting point, your machine precision errors, if they all conspire against you, it's possible to wind up stuck at a sort of false fixed point in theory. Never happened to us, as far as we know. And basically, what we always found is that using this procedure for updates, we do wind up at the correct fixed point. Our row does eventually converge to the correct one that we wanted. So
what you're saying is that obviously there's a possibility of introducing new fixed points by this approximation, but they're typically all unstable, or they don't exist.
All I'm saying is, so far we've never hit one. Well, we've never seen a case where we've got a mirror that runs well sometimes and then sometimes gets stuck in a false fixed point. It's basically a case of either it works or it doesn't. If it doesn't work, it's because you, say, truncated too much and lost the essential character of the Hamiltonian by setting chi ridiculously low. Trivial example, set chi equal to 1, you'll nuke anything.
You get slowdown sometimes? I mean, you can imagine if you were close to a settle point, you might get a slowdown as you pass through it or something.
This, again, can happen in both theory and practice. It's not uncommon in tensor network algorithms to see, say, an energy converging like so, where you have a bit of a plateau before you actually reach the ground state. So, if in doubt, run your simulation for longer. All we can ever say is that we know the ground state has an energy that's no greater than this one.
So it's variational?
Yeah, all of these ansatz, variational ansatz, are constructed so that they give you an upper bound, because they explicitly give you the wave function. You know that there exists, and compute the energy for that wave function. You know there exists a wave function with this energy. And so the ground state energy is at least this low, possibly lower, but no higher than this. And that's the way that these ansatz always work. Actually, with PEPs, it's even slightly more difficult because computing expectation values is difficult. I haven't talked about PEPs. It's a 2D generalization of MPS. And sometimes there's actually approximations used in computing, say, ground state energies with PEPs. In fact, one thing that people are doing is using Monte Carlo to to compute the energy of a particular PEPS tensor network because it's very expensive to compute exactly. But the ones I've been talking about, mirror, tree tensor network, TBD, MPS, you can compute you have an exact description of your state, and you can compute the ground state exactly at a reasonable cost. And so you basically know that you've got an upper bound on the ground state energy. Now, doing the scale-invariant mirror in practice. So you start at the bottom. So you start off with an initial set of random U's and W's and a Hamiltonian at the bottom. First thing you do, lift your Hamiltonian up all the way, create an initial reduced density matrix, bring it down all the way. Or just set those up randomly as well if you like to start with. It really doesn't matter too much. You're going to fix things when you start iterating. So you've got your Hamiltonian at the bottom. And you've got a Hamiltonian on all levels and a reduced density matrix on all levels. So you start at the bottom, take your Hamiltonian and the reduced density matrix on the coarse-grained lattice, update U and W at the bottom here, lift your Hamiltonian up, using the reduced density matrix on the level above again, update U and W here, lift your Hamiltonian up, same here, lift your Hamiltonian up. Scale-invariant layer, you can either treat it like any other layer, or once things have started to converge, you can help yourself a little bit by getting rid of a few more of those irrelevant terms in the Hamiltonian and lift it through this layer a few more times before you actually optimize this, through the scale-invariant layer a few more times before you actually optimize this. Assuming your scale-invariant layer is reasonably converged, and is therefore projecting out irrelevant components of the Hamiltonian, then lifting it through a few more times is going to suppress those even more. Means you get slower convergence, but your irrelevant terms are suppressed more. So your scale-invariant layer is acting on something that's closer to the true fixed-point Hamiltonian, and that means that this represents the low-energy subspace of that fixed-point Hamiltonian a bit better. And you've got your reduced density matrix up here at the top, which I just explained that to update it, you lower it through the scale-invariant layer, then put it back at the top again. And then you lower it down to get all the ones on the layers below. So, that's, in a nutshell, how you do the scale-invariant mirror. How you compute the scaling dimensions? Well, you take the scaling superoperator, which I drew out for you earlier before I stuck rows on it over there, and you diagonalize that. Basically, you can use the Landshaw's method for that. There's actually a shortcut for that on the 3-into-1 mirror. This is why we like the 3-into-1 mirror so much. If you look at a 3-into-1 mirror, there are some special privileged sites. And I'm just going to point out one of them here. If you look at this site here on the lattice, then we do a 3-into-1 coarse graining. It only hits an isometry. It doesn't hit a disentangler. Same again on this level, and so on up. Now, if you pick your site just right, then in theory it could be sitting under an isometry all the way up forever. And so an operator on this site, a one-site operator on this site gets mapped into a one-site operator on the lattice above, and a one-site operator on the lattice above that. And it gets mapped on, and the mapping for that is performed by this scaling superoperator. Because the disentanglers on either side between bra and ket are going to cancel when if you're computing the expectation value of this operator, then the disentanglers on either side are going to cancel, the isometries are all going to cancel. You're just left with something which looks like this that takes that operator from layer to layer. And that's very nice, because you can diagonalize this little operator for a cost of chi to the 6. And that will give you a one-site representation of this. That will give you one-site local scaling operators. Formally, these correspond to a one-site representation of the what's the name of the Virasoro algebra that describes the scaling operators in the conformal field theory. If you diagonalize the scaling superoperator I drew over there, then instead of getting one site bunch of scaling operators, phi, sort of phi alpha, you get a bunch of two-site scaling operators. Good news is, though, we're dealing with a critical theory which corresponds to a particular conformal field theory. Doesn't matter which representation of the, well, which set of local scaling operators, and therefore which representation of discrete, so which discrete representation, which representation of the, well, it's a truncated representation of the Virasoro algebra that describes the scaling fields. It doesn't matter which representation you go for, it's going to be describing the same conformal field theory. So we can just go for this one-site set of operators and associated scaling dimensions. And we can calculate, and that's really cheap. It's much cheaper than our actual update process. So we can calculate that on the fly every single iteration, just to keep an eye on how things are converging. If you want to calculate these guys, they're more expensive. This costs chi to the 10. And you may get a few more digits of precision, but usually these guys are pretty much all you need. So that's how we calculate. And now, when you diagonalize this, you get a bunch of operators, phi alpha, with eigenvalues, with associated eigenvalues. But what you want to extract is scaling dimensions. I'm not going to explain the conformal field theory stuff right now, but I'm going to explain how you get the things that we're after, which is like, for example, the scaling dimension. So you take your operator, and it's got an eigenvalue, phi alpha, and it's got an eigenvalue lambda alpha, and your scaling dimension, and that lambda alpha corresponds to 3 to the minus delta alpha. 3 because, or delta alpha is the scaling dimension. 3 because we're doing a 3-into-1 coarse graining. And so basically, to get out your scaling dimensions, what you do is minus log base 3 of the eigenvalues. Now, what's the easiest way to explain why we get 3 to the minus delta? Let's see. Right, so now I have to go a bit too much into the conformal field theory to justify that relationship. Probably tell you a bit more what delta alpha actually is. And I'm trying to keep this to be a talk about how to do the mirror rather than how to do conformal field theory. I've got about 15 minutes or so. I kind of wanted to mention the boundary mirror, so I'll let people bug me about conformal field theory afterwards if they want to. The boundary mirror is kind of interesting because what you have here is you can have a lattice with a boundary, so it's infinite in one. So for sake of argument, we'll consider one which is infinite in one direction. So we have a boundary and it's infinite from a point. This too can be scale invariant. This point, under coarse graining, this point at the boundary stays as a point. And a region of length L, for example, may get mapped into a region of length L over 3 under a sort of a scaling by a factor of a third. But because the entire lattice is infinite, well, because if we're dealing with a field, we've got an infinite continuum in this direction, so we've still got an infinite continuum. With a lattice, we've got an infinite number of lattice points, so again, we have an infinite number of lattice points. And so we should be able, we hope, to do a 3-into-1 mirror on this as well. Now, what we want here is we want an ansatz where the bulk of where we don't have to, well, basically we can keep our nice property of using the same disentanglers and isometries for most of the ansatz. Translation invariance along the infinite portion of the ansatz. What this means is that if we're going to have any different tensors in there, they can only differ at the boundary. And the region which differs has got to basically stay the same under coarse graining. So to give you a better idea of what I mean, we're going to have something like So hopefully what you can see here is that what I've basically done here is I've drawn an ordinary mirror at something of a slant. That was just, the fact that it's slanted isn't hugely important. It was just a matter of conveniently fitting it in a way that was easy to draw. I could have just gone for the usual thing of making it more cramped as I went down. But basically what we've got is we've got an ordinary mirror here in the bulk, and we've got some special isometries here at the edge, which only have two legs. We've cut off basically one side of the diagram at this column of isometries. Now, there's basically two choices we can make that leave things that basically gives us scale invariance. One is fairly obvious. If we introduce a local scaling operator, if we introduce some sort of operator which we hypothesize to be a boundary scaling operator here, and it's a one-site operator, then to map it up to the next level, this one-site operator maps up onto just this site here. So it's like, if you follow up the possible sites it can reach, if we go through the isometry, it comes up to just this site. So that will be a one-site representation of the boundary conformal field theory. And for this one, we would just change, we would have these isometries here would encode the information about the boundary scaling operators. And then the rest of the tensors would correspond to the bulk of the theory, and we'd hypothesize that we hypothesize that a good representation of a boundary conformal field theory can be obtained by setting these to be the same tensors as we'd use without the boundary. If we just looked at a model with no boundary, just on an infinite in both directions lattice. So what you can do is you can start with an infinite lattice in both directions, construct a scale-invariant mirror on it, optimize the disentanglers and isometries, and just plug them into, and just take those and use them here. Once they're optimized, they converge, you just take them and keep them, and that's your tensors for the bulk. And now all you need to do is optimize these ones along the edge here to get a representation of a boundary conformal field theory, which gives you some boundary operators on one site, B alpha. The other alternative would have been to take two-site operators. Now these ones would map also again into two-site operators. So again, we have two-site operators mapping into two-site operators. But for this one, the things that could be different also are the isometries, two isometries at the edge and one disentangler. And so we also have a way of getting a two-site representation of the boundary conformal field theory. In practice, the one-site one works just fine, so we tend to stick with that. If you go up to more sites, like if you go up to say 3 sites, then that gets collapsed down to 2. So, like a 3-site operator here would get mapped into a 2-site operator here, so you'd end up with a 2-site representation again. That's just the property of the of this particular ansatz.
Won't all operators eventually 2 at most.
That's right. This is one of the things that makes the mirror particularly tractable. Basically, anything that you start off with quickly gets reduced to a two-site operator, which is what the tensor network is designed to handle efficiently. So you can actually say operators on 3 or 4 sites, and you'll find that they rapidly get reduced to a 2-site operator, which is what you then actually. So you compute that 2-site operator, and then you actually use that as your starting Hamiltonian, say, when you're simulating the mirror. This is a property that you'll see referred to in papers on the mirror called fixed width causal cone. Yeah, very useful property. It's what makes everything possible. It's what means that, for example, when we're taking a 2-site operator and we're lifting it up to the next level, it stays a 2-site operator. That's what makes it possible to do the mirror. So this is the idea of the boundary mirror. Has been applied to some critical theories of the boundary, and there's a paper on archive on this. I think Glenn's working on a second paper on this as well, where he looks at things like chains with Y junctions. So, yep.
So, just before you started talking about having just 2 types, I would think, naively in general, you might have an index going away from this edge, and then eventually into some region in the bulk you converge, but the number of operators that you need to have that are unique, well, at least before you talked about it, it wasn't trivial that it would only need to be 1 or 2 types.
Yeah, you'd think in principle that it might have to be infinite, and that you'd approximate at some distance, you'd cut off and say it's close enough. In fact, this is what happens with the reduced density matrix. If you were to compute a reduced density matrix on say, these 2 sites here, then these 2 are in the bulk, but your reduced density matrix is going to receive take these 2 sites here. They're in the bulk, if we're just working with the orange ansatz. These 2 sites here are in the bulk, but the reduced density matrix here receives contributions from the one on these 2 sites here, which is on the boundary. And so what you see is that if you're computing expectation values, for example, then your reduced density matrix, no matter how far into the bulk you are, your reduced density matrix, after sufficient layers of coarse graining, is eventually going to receive contributions from a reduced density matrix on the boundary. So the boundary influences properties on the bulk. For example, correlators between boundary and bulk, or correlators between boundary and bulk. Basically your reduced density matrix is always influenced by the presence of the boundary. This is how having a particular boundary can actually affect the spectrum of scaling operators that you see in the bulk.
But that's true of even a bulk-bulk correlator will eventually be affected by the density matrix of the boundary.
Yeah, that's right. Yeah, even a bulk-bulk correlator will be affected. And this is in fact what you'd expect from the conformal field theory, that there would be that things are influenced by the presence of the boundary. So why can we? So there's 2 things here. First is that we say, let's take this as our assumption and give it a go, that these are all the same, and see if it works. Answer is it does. Second one is, because the mirror has this fixed causal cone, if we started off with, say, 4 tensors different down here, then those 4 tensors, when we coarse grain, we're only going to need 3 tensors different on the next level, or 2 tensors different on the level above that. And so we see that fairly rapidly, for any finite number of tensors different, we're going to reduce to just having a small number different on the boundary. Yeah, 2 eventually. Typically we'd end up with 2 isometries and a disentangler different at the boundary. The fact that we can do it with 1 is basically fortuitous. It's a nice piece of luck that we can do it that way, or a nice piece of construction. But if we were to try and get there by convergence, we'd probably end up with the red one rather than the orange one. Anyway, if you now say, suppose that we took them all different, I'm going to say, okay, I'm going to go out a ridiculously long way to where they're virtually the same as the bulk. I'm going to truncate and I'm going to make them the same as the bulk beyond that point. You're not going to be able to tell the difference at any numerical level you're going to be concerned about. And now I've got only a finite number of tensors, and I'm going to coarse grain repeatedly until I've got this situation again. And so that's why I suspect, and that's why it turns out that these guys, taking these guys from a bulk simulation, well, from a no boundary simulation works just fine. You can actually put boundaries on both sides of an infinite number of lattice sites as well. That requires a little bit more trickery to take into account the effects of both boundaries on your correlators. You have to start an infinite distance up to where you actually get.
It's an infinite length lattice with two boundaries?
Yeah.
All right.
There's an infinite number. Okay, it's like, imagine you've got a finite length of line with a boundary at each end. There's no you can fit an infinite number of points on that line, and that's basically what you're doing. But to take into account the effects of both boundaries requires a little bit more trickery, because you have to start an infinite distance up your mirror where your reduced density matrix will contact both boundaries. You have to take both boundaries into account. So that's trickery, yeah. I guess the last thing I should probably do before we finish is give you a few useful references. So I talked about the Suzuki-Trotter decomposition. Here's Suzuki's paper on it. It's Journal of Mathematical Physics, 26601, volume 26, page 601, 1985, author M. Suzuki. Now, so Embley, algorithms for entanglement renormalization. Check that I've got the latest. This is the right one. Yep, this is. This is the paper on how to do entanglement renormalization, also available on arXiv. So yeah, G. Evenbly and G. Vidal, Phys. Rev. B. 79. 144108. And that's archive number. I should change board. Oh 0707.1454. That's in CondMat, I believe. Yeah. Scale-invariant mirror. Pfeiffer, Evenbly, Vidal. Scale-invariant mirror. Oh 40301, and that was year of publication. That was Again, available on archive. And finally, the boundary conformal field, so boundary mirror. Boundary quantum critical phenomena with entanglement renormalization. This one is so this is one of those papers where the author list is longer than the title. PhysRev B 82.161.107. Also on archive. Okay, so that's a little bit of supplementary reading if you want to get more details about any of the mirror parts of this talk. For TEBD, I believe there's a couple of good review papers out there. I don't know how didactic they are because I learned TEBD from conversations within the research group at the University of Queensland. So I'll leave you guys to search if you want to look for something written on that. Okay, end of talk. Any questions? Oh, and I've got an assignment for the people who get excited about such things. I'll give Roger one because I'm sure he'll want to do this. Here's one for Anne. You can all have one. I've got enough to go around. Of particular interest here, I guess, well, something that might be particularly useful is I've included a MATLAB function tcontract. Now, in general, if you're going to contract a couple of tensors together in a computer code, you're probably going to want to just iterate over all the indices using for loops, for example, in C or C++. You'd iterate over all the indices using for loops and just work out each term of your sum using those for loops. Now, nested for loops in MATLAB are very slow. So rather than making and the point of this assignment is to implement TEBD, not to scratch your head over how to contract tensors rapidly using MATLAB. So I've provided this little function which does it efficiently. If you program MATLAB, it's well worth taking a look at this function because the principles, the ideas in there are pretty useful to be familiar with. Basically, it uses the reshape and permute commands to turn any tensor contraction into just a multiplication of two matrices, which is handled by the BLAS library, and so is fast. So it's a way of doing multiplication with MATLAB of doing tensor contraction using MATLAB primitives rather than using for loops. And yeah. Just as a sort of little refresher just to remind myself how long it would take to do this, if you knew exactly what you were doing, I implemented TEBD from scratch myself just yesterday. Took me It took me about sort of hour and a half, 2 hours writing this at the same time. So probably going to take longer as an assignment because you're not familiar with this stuff. So if you want to do this, whether you're doing it as a course or not, come and bother me plenty. Come and ask me lots of questions because I'll be keen to help. Always nice to have other people getting started in tensor network algorithms. All right. Ah.